All right. Well, we're going to do part 2 of this. Last month we did part 1, and I've really been fortunate in that throughout my career, whether working for Monsanto, Solutia, Emerson, or now Mina Technologies, I've been encouraged to go ahead and document what I have learned, and I've also had the freedom to spend time exploring, discovering, and then what's really important to me, sharing that knowledge. So it's been a very fortunate and perhaps unusual career. Last month we did go over the basic types of processes, and the most common type of process is self-regulating. It's simply because a flow loop is self-regulating, and there's probably more flow loops than any other type of loop out there. But for a flow loop, the response is very fast, and we kind of know how to tune those things, and it's kind of forgiving often in the tuning, and so it doesn't usually need much study. The more interesting processes to me that are self-regulating are for composition, temperature, and pH control, and they're on liquid volumes. It could be vessels, there could be columns, and the response is much slower. Instead of seconds, it could be hours or days, even in the case of some big distillation columns. And we get into a situation where the time constant is very large compared to the dead time, and that's what we're showing here is a first order approximation. By first order, we mean we're approximating the exponential response by a single time constant. And so after the process gets out of the noise band, and then when it reaches 63% of its final value, that's the time constant, and we hope it's in the process, and if it's a negative feedback time constant in the process, it means you reach a new steady state. So if the controller is in manual and you have a disturbance, or in this case a change in controller output, it'll eventually go to a new steady state. That's assuming you don't make more changes in controller output, or there aren't more disturbances happening. So the process has self-regulation, and that makes it, in some ways, easier to deal with, and has a lot of implications in terms of what we have to do for tuning. But actually, what I've found out that's interesting for these slow processes that are more inches, like vessel and column, temperature, pH, and composition control, what we have is a near integrating response, in that the time constant is more than 4 times the dead time. So in this time period where the controller is trying to do most of its action, which is like 4 dead times, normally if it's well tuned, it just sees a ramp. And so it's near integrating. It doesn't do it. It's not going to see the steady state unless you do this open loop test, and you do this open loop test for these type processes. It's going to take a long time. So there's an advantage, first in terms of the test time, to recognize all I need to do is get this ramp rate, and second of all, I need to realize I should be understanding this process, analyzing this process, and also tuning the controller based on it being a near integrating process. So the near-integrating process looks like a ramp in the time frame of the PID response. The equivalent open loop time constant, the equivalent open loop integrating process gain is equal to what was the steady state process gain, K sub O, divided by this very large process time constant. And we go T sub O, or tau sub O, where the O stands for open loop. Anyway, we can go back and forth between an integrating process gain and the equivalent time constant, large time constant, using this very simple equation. In fact, it's been around for many, many years. In fact, they didn't originally have tuning rules for integrating processes, so they would convert it back to an equivalent self-regulating process, and there they would just go with a K sub O equal to 1. because they were trying to focus on what figuring out what the time constant was, unless they had some additional information. A true integrating process doesn't reach a steady state if the controller is in manual, and it just continues ramping. In fact, once you put the controller in manual, it'll be ramping. And so you make a change in controller output, what you're going to see is a change in ramp rates. And so the open loop integrating process gain really is based on that change in ramp rates divided by the change in controller output. Notice that everything here is in percent because that's what the controller PID algorithm works in, is in percent. And so it's very important if you do any estimation of these dynamics that you get the right units. And for the integrating process gain here, it's percent per second per percent. And what they do in the literature is cancel out the percent, so they just say the integrating process gain is 1/seconds. And the steady state gain, if we went back to the other slide, it would be percent per percent, percent PV change per percent controller output change, and it would be dimensionless in the literature. And the time constant can be in minutes or seconds. You just got to know which one. Then we have a runaway process. They're not very common, but boy, we need to understand and deal with them properly when they do happen because they're very dangerous. Typically, it's a polymerization reactor where the reaction rate is very high as the temperature increases, which then causes the reaction rate to increase, causes the temperature increase, and it runs away from you, and as a result, it can cause relief valves to burst, or hopefully to blow, rupture this to burst, or even worst case, there could be high temperatures causing significant failures of equipment. Anyway, this acceleration is rarely seen because we don't do an open loop test. This would not be safe to do. So we terminate that test before we probably see the acceleration. Now, the time constant in this case is a positive feedback time constant causing this acceleration or runaway, and you really can't measure that well, although we've got it shown here theoretically, because, as I say, you can't do this open loop test as a practical matter, but you can get it from some very simple ordinary differential equations, which are typically given in Appendix F of many of my books. And so you can understand where it's coming from and what could affect it. And you want this positive time constant to be very large to slow down this acceleration that you might see. So what are examples? Here, integrating process, continuous column, composition and temperature control, and wherever I say composition, I should also have said pH. pH is a composition, but we don't tend to think of it that way. So whenever you see composition here, just also think of pH. Continuous vessel composition, temperature control, crystallizer, evaporators, fermenters, neutralizers, reactors. True integrating processes, example, classic is level, where the level will ramp based on the difference between the flow going into and out of volume. Then, not probably realized is that batch column composition and temperature control, and also gas pressure control tends to be a true integrating process. And here, not only for columns, but for vessels. And we got the same list of examples for vessels. Runaway processes, the classic, as I mentioned, is polymerization reactor, temperature control, highly exothermic. But there are some others which we don't really tend to see because they're not really doing the closed loop control, and it's a very slow acceleration that we might see with the exponential growth phase of cells. As you get more cells and they're growing and reproducing, they produce more cells, which then increase the concentration, which increases the growth rate, production rate of new cells, and so on. So you could potentially, if you looked at it and had closed loop control, see and classify it as a runaway response. One I personally have seen that's very fast, incredibly fast, everything happening in a fraction of a second, is an axial speed where the precipitous drop in flow at the start of surge caused an acceleration within a fraction of a second. We had to have an analog and derivative module detect the rate of change of speed to shut down the compressor to protect it from self-destructing. Strong resonance, strong base, it's not a true runaway, but if you look at the acceleration as you approach the 7 pH point, it can look like one to the PID. And you know, you got to realize what the PID sees is really how you got to think of how to tune it. So this can be a consideration. There are many loop objectives. Key thing is to realize there's a final resting value, and final resting value is where the PID output ends up for a self-regulating process after a disturbance if you're in automatic, or for a set point change you're in automatic. And it's very useful to in terms of, in some cases, it being a metric, but also if you wanted to calculate the open loop process gain, you can do it in a closed loop fashion by making a set point change and looking at the change in PV or set point once you settle out and divide it by the change in the PID output, and that can give you the steady state gain. So it has a lot of uses, and in some cases a metric. Here we're going to look at some of the key loop objectives. There's probably some more that I don't have, but for me, minimum peak error in load response was critical to prevent compressor surge, safety, instrument system activation, relief undesirable reactions, poor cell health. Cells are very sensitive to high temperature. They can start to die very quickly if the temperature just gets a degree or two above what they want. Then we have something that's more out there in the literature. It's the integrated error, and it can be associated with load or set point response, but normally in the literature it's associated with load response. And it minimizes the total amount of off-spec product to enable closer operation to the optimum set point. We also want to minimize overshoot of the set point and set point response to similar to the peak error, some of the same things, same considerations. For bioreactors, particularly mammalian cells, they are very sensitive to overshoot of a pH or a temperature set point to way beyond what I would have expected. We're talking about a tenth of a pH or a tenth of a degree C being significant in terms of overshoot. And then we have a situation where we want a minimum output overshoot of the final resting value in a set point response. And this is principally to prevent interaction with heat integration and recycle loops. And this is a common occurrence in hydrocarbon gas unit operations. And so the focus may be on there. And I've seen an article where it thought that was the only thing you ever needed to do in process control, was to focus on preventing overshoot of the final resting value, not realizing that if you have an integrator, the only way you can deal with a disturbance, the only way you can make a set point change is the output has to go past the final resting value. If you think of a level loop and you have like 100 GPM coming in and 100 GPM going out, and you want to raise the level, well, you've got to go past the final resting value of 100 GPM and maybe raise it to 150 decrease it to, say, 50 GPM coming in to raise the level up. Also, if you're at balance at 100 GPM in and out on a level loop, and you get a disturbance, another flow coming into the tank starts to increase, then you need to deal with that, and you end up and I think if in this case if you're manipulating a flow going out of the tank, you have to deal with that change by overshooting typically the final resting value. the minimum time to reach set point and the set point response, and I ran into this because of the batch cycle times I'm involved with were in the order of hours, and then also for startup times, trying to minimize those, and transition times between new products and operating rates. And then split range crossings, you want to minimize those, and it turns out if you have a low demand for energy, reaction, or reagents, you're probably going to be oscillating across the split range point due to the severe discontinuity in terms of changes in process dynamics and a higher degree of stiction and backlash that exists near the seat. So it tends to oscillate, or quite common, and so we want to minimize those to prevent going back and forth between heating and cooling or acid and base reagents, and also for cells in terms of unnecessarily adding sodium bicarbonate, building up salt concentration causes high osmotic pressure, and so you don't want to going back and forth and then building up the salt concentration, where sodium bicarbonate is the weak base being used for pH control. Anyway, another key thing is maximum absorption of variability and level control. A lot of processes are oscillating due to some level control loop. They're not being tuned properly, and in a lot of cases, it should have been tuned so that it wasn't really so tight level control, but you were minimizing the flow that was manipulating, typically a flow going out of the volume, and that flow going out of the volume then is upsetting other unit operations downstream. So you want to absorb the changes in variability in terms of level as much as possible to reduce the amount of changes you make in that manipulated flow going out that is affecting downstream unit operations. And really what it comes down to in a lot of loops is the optimum transfer of variability from the controlled variable to the manipulated variable. I mean, we'd like to think that maybe variability disappears, but what does a control loop do? It transfers the variability from the process variable to the manipulated variable, its controller output, based on the tuning. And where we want tight control, we want to be close to set point, we transfer them a lot of variability from the control to the manipulated variable. Where we want to maximize absorption variability, like just mentioned, we want to minimize that transfer. And if because changes in the manipulated variable upset other loops. And so there can be an optimum for different situations, and we will learn some PID options that will allow you to smooth out those changes in the manipulated variable that may be affecting other loops, even if we're not talking about maximum absorption variability for level control. So we're going to see about a PID option that will help us there in terms of changing the manipulated variable and not upsetting other loops. So we got different worlds. We have hydrocarbon processes, and I'm not going to go into the details here, but you can see the different objectives and characteristics they have. I came from the world of chemical batch and continuous processes, although I worked also on utility systems and on polymer and sheet lines. So I have an understanding and extruders understanding of some of the requirements there. And also I worked on biological vessels, fermenters, and bioreactors. Not mentioned here is mineral processing, as Michelle Ruel said, and there's some control talk columns on that that you can read to get an idea. But the big problem there is a lot of noise and difficult measurements. In fact, it may not be a representative measurement, and the process dynamics can get very weird. In fact, it's not maybe identifiable, and it can even change the process gain, can change sign. And so Michelle Well actually reverted to some fuzzy logic control. But it is a challenge due to the difficulty of the measurements and the noise and sometimes the strange behavior in the dynamics for mineral processing. And then we have a new protege in our program from the steel industry, Mohammed Asafi. I included him in the distribution for this WebEx, but I didn't give you the official introduction, which I will do tomorrow. Anyway, we hope to get some indication then of what are the requirements in the steel industry. This is a control loop. It's very useful for finding out the source of dynamics, realizing that while the literature may talk about a process gain and a process time constant, process dead time, really what they're talking about is a open loop gain, an open loop time constant, an open loop dead time, and what contributes to that open loop characteristics that we do in terms of first order approximation is the individual delays, lags, and gains. And so you got to multiply all these gains from the valve and the process itself and the measurement to come up with the open loop gain. And we got to understand then the contribution of the valve characteristic and its slope for the installed characteristic, giving us the valve gain. And then we got how the process gain changes with operating conditions and flow rates. And the measurement gain is pretty well fixed because it's set by the calibration span. And so that open loop gain is really the product of gains from the different major parts of the control loop, the valve, the process, and the measurement. Now, the largest time constant, wherever it is in this loop, is the open loop gain. We want it to be the primary lag in the process as shown here, tau sub B. We want it to be right here, but it may not be. In fact, in flow loops, it probably isn't. It's probably associated with some filter we have here. Similarly, the delay here may not be the largest delay in the loop. It could be the delay associated with the execution of the controller, or the delay associated with the response of the control valve, which we've seen can happen for particularly poor positioner designs or for valves with a lot of stiction or backlash. Anyway, it really is useful to understand where the dead times come in. You want to find the biggest source of dead time and reduce that. You want to understand what creates nonlinearity by realizing that we have a product of gains going on here, and also in terms of trying to maximize the open loop time constant being the primary lag. And this is the principal source of disagreement in process control. In the literature, typically when they develop, internal model control and even lambda tuning, the idea was that this time constant was not that much bigger than the total dead time. And they didn't put the disturbance here, but they put the disturbance on the output. Now, if this time constant is not too large compared to the dead time, it doesn't really matter where it is. But it turns out for the type of processes, particularly that I was involved with, the disturbance really comes at the input of the process. And this time constant can get quite large, and leading to a whole different analysis and some problems with the traditional use of some tuning techniques and analysis techniques. We're going to be talking a lot about it. We've already talked some about it, but we're going to be talking more about it as we go through here, because it has created so much disagreement and confusion. And again, like I say, the literature really deals mostly, say, with this time constant being about the same size as the total dead time. Well, we're going to finally get to the reaction of the PID controller. And here we're focusing on the response of the PID controller itself. So while there is a measurement, it is not changing. All we're seeing the effect is the set point change. And furthermore, the set point doesn't have a filter on it or a lead lag, so we're getting a step change in set point. And we are using a structure PID on error. So we're going to get a response of the proportional, integral, and derivative modes to error, which means also to the set point change. So we have a step change in set point here. We get a step from the proportional mode. And we get a kick from the filter derivative mode. Now, if there is no filter on here, and normally there's a built-in filter that is 1/8 the rate time. But if there was no filter, this would be a spike, and it could be very, very large. Some PIDs and some PLCs may not have this built-in filter, and somebody can adjust this filter and maybe have set it to 0 or to a smaller number, not knowing the consequences. Anyway, if there is a filter, what you get is a kick that decays rather quickly. Its contribution decays to 0. And what you're left with is the contribution from the step and the proportional mode and the ramping action that you get from the integral mode. Now, when you repeat the contribution from the proportional mode, and that's what's shown here, the change in controller output here too is equal to the controller and change output number 1 that we got initially here from the proportional mode, we say we have got a repeat from the integral mode. That time to do that repeat is seconds per repeat, and that is the setting of the integral mode. Now, in a lot of PID controllers, they don't tell you it's seconds per repeat. They just say seconds. Other PID controllers use the inverse, and then they will say repeats. They will say repeats per second or repeats per minute. So you need to be very careful with understanding what are the units, particularly of the integral mode. For the proportional mode, it should be a gain and it should be dimensionless, but there is a proportional band that's still used in some controllers, and you have to convert from proportional band to controller gain. And proportional band is like how much of a percent change in controller output, controller process variable is needed to give a 100% change in controller output. So, if you say only 50% change in process variable is needed to provide a 100% change in controller output, the proportional band is 50%. If you say the proportional band is 1%, that means you only need a 1% change in process variable to get 100% change in controller output. That would correspond to a gain of 100. Now, I'll get into some war stories probably in November that will give you some very interesting scenarios where people didn't realize this, and they went from a controller with a proportional band of 100 and didn't realize, now they're dealing with gains, and that would be a gain of 100 that they're putting in there. Unfortunately, it was a level loop on the column, and for that type of application, for controlling reflux to the column, it made the column work that much better, and they thought it was all due to the migration project, when really it was just due to misunderstanding between proportional band and controller gain. Now, what we got to realize here is that even though the set point hasn't changed and the process variable hasn't changed, the output is continuing to ramp. And considering that the error is never exactly 0, the output is always moving from integral action. And this can be a problem. There's some other problems with integral action as well, particularly for processes that take a long time to reach steady state or have no steady state. Now, if there's no change in the error, no change in the set point, no change in the process variable, there is no change in terms of the contribution of the controller output from the proportional mode or from the derivative mode. And one last thing is that, some processes, they don't like this step or this kick because it is upsetting other loops. You can use this PID option I'm going to talk about to minimize that, or you can use different structures to minimize that as well, not have PID on error. Now, the thing, you need to realize, if you want to get to set point faster, this step change in the controller output is going to help a lot. Now, the kick you get from derivatives, since it's temporary, doesn't help an awful lot in terms of getting you set point faster, but it helps get through the backlash and stiction of a valve. And so it can be advantageous from that standpoint. Now, it's interesting, the hydrocarbon industry and for very fast self-regulating loops, we don't have this concern with reset time. But like for the more interesting loops that I was talking about, at least to me, in terms of composition, temperature, pH, and control, and level control, and gas pressure control, you can probably go into a control room where there's a problem in terms of control or tuning, and just by increasing the reset time, in other words, reducing the amount of reset action we're talking 2 or 3 orders of magnitude, the loop stabilizes. And furthermore, this is a general situation where it's not going to hurt you. It's not going to make something unstable. It may, if you really didn't need to do that, it's going to slow down the response to some continuing disturbance. Reset is particularly helpful if you've got a disturbance that just keeps growing, and so you got to keep driving that controller output to try and catch up with it. But for that step disturbance, typically the way we look at control loops, then we got to realize that we really are not doing us any good by having this excessive reset action. And it turned out it tends to be what happens for a variety of reasons, and one of them is exemplified by this application. So we're going to consider, should the steam or water valve be open for this liquid reactor? We have a situation where we have a faceplate, and the process variable says the temperature is 48 degrees and the set point is 52 degrees. And the question is, just looking at that faceplate, should the water valve be open or should the steam valve be open? Several different control rooms made a complaint that there's something wrong with the PID algorithm, because for this scenario here, as the operator was very attentive and looking at this faceplate, he said, good grief, the water valve is open and here the temperature is 48. I'm waiting for this. It's a slow temperature response, which is kind of typical for a big liquid volume. I'm waiting for that temperature to come up, and that darn water valve's open. What's wrong with your PID algorithm? Well, if the operator had a good trend, and that's problematic, having a good trend in terms of the right time scale and process variable scale, to zoom in here, he might understand that you look at this trajectory here, and it needs to open the water valve, because any action that's taken, you got to remember, doesn't have an effect on the process until one dead time later. So it needs to take action now to prevent overshoot. And if it had the steam valve open, this is what you would get. It would be severe overshoot. Now, what does integral action do? Integral action says, until I cross set point, I want that steam valve open. So it's working to keep the steam valve open because the temperature is below set point. Proportional and derivative action is saying, whoa, man, you're approaching the set point. I got to get that water valve open. If the integral action dominates, the water valve won't open until the error changes sign. And then, is it enough? Probably not. It's just starting to open, and then it's going to be one dead time later before you see the effect on the disturbance. So looking at digital values, humans think steam valve should be open in this case, which is what will happen if there's more reset, more integral than proportional gain action. So we tend to tune loops often to, based on what we're expecting here, not realizing trajectories and the consequences of dead time. And particularly if the operator is focusing on the faceplate and doesn't understand trajectories. Now the new operator interfaces are giving arrows, and there's a size of the arrow, and the arrow tells you whether the process variable is increasing or decreasing, and what rate based on the size, I think, or boldness. What really is needed is this trajectory here, and we have a way of computing this future trajectory very simply based on the slope here, and then multiplying that slope by the dead time and adding it to the current value, and we can give the operator a trajectory, one dead time into the future, what's going to happen. I think that would help a lot in terms of operator understanding, and also in terms of tuning controllers. So for me, the metrics and objectives have often been peak and integrated error and for load response. And so I concentrated on trying to get equations that would help me there. But first I needed to know what is the best you could do. And the best you can do for a load disturbance, and it's idealistic because you really can't do this, is this triangle here. And it's actually two right triangles placed back to back, where the base of that triangle is the total dead time. And the height of that triangle in terms of the ratio of the peak error to the open loop error. The open loop error is if the controller was not an automatic, what would be the error you see? And so the idea of having it in automatic is you're reducing that peak error. And so we're looking to, in this situation, a self-regulating process, what would happen if we had a step change in a disturbance and we then didn't have a controller in automatic? We would have an open loop error. And then we say, well, if we put that control in automatic error, how good can it do in terms of reducing the size of that open loop error? And that's this ratio. And that ratio turns out to be the best we can do for this ultimate capability is the ratio of the dead time to the dead time plus time constant. Now, what happens if you have a very large dead time process? And in some process industries that can happen. Not as often as you might think, but as that happens, then this ratio approaches 1 if the dead time is very large compared to the time constant. What we have in near integrating processes is a very nice situation where the process time constant is very large compared to the dead time, and this kind of reduces to a ratio of the dead time to the time constant, showing us we have great potential if we know how to tune the loop. Now the area here of this best case idealistic scenario is the integrated error. And it is the ultimate limit to what we can do. Now, if we have a reset time larger than really what we need or should have, then the return is, the set point is more gradual. If we have a gain that is too small, the peak of this triangle is going to be larger. So the ultimate limit to rejection of unmeasured load disturbance has a peak error that is height of an integrated, that is the area of two right triangles placed back to back with a minimum base width that is 1 dead time. In practice, the tuning needs to be more robust, and each base is probably 2 dead times. The time to reversal the direction of the PV, that's right here, and start of the approach back to set point, is the arrest time, which is lambda for integrating process tuning rules, which is why we like to switch to integrating process tuning rules when we have a near integrating process where we have a very large time constant, for many reasons. In gamesmanship, proponents of tuning methods and software show how close they can get to the optimum simulation test when in reality plants are too nonlinear and non-ideal to make this realistic. The real value of the figures and associated equations is in the realization of how dynamics and tuning relatively affect performance. And to give you an idea of all the different tuning rules and how we get obsessed with them, really, and we're not focusing on understanding the principles and applying fundamentals, you can go to this white paper. Then for some processes that I was involved in where the batch cycle time was in the order of hours, and also we wanted to minimize startup time that was maybe even less than an hour of transition time. We looked at metrics of set point response, and so I was interested in getting to set point as fast as possible, but with minimum overshoot, and that overshoot here is E sub x1, and then also minimum undershoot, E sub x2. And so this was kind of a challenge, because it turns out if you literally use the tuning settings for best load disturbance and a PID on error structure, you're going to get overshoot. The solution, give you kind of a heads up, is that you can choose a different structure like proportional on error, but that kind of really slows down the approach to set point. Probably better is a set point lead lag, where the set point lag time is equal to the reset time, and then the lead is equal to maybe about 25% of that. Kind of a simple thing to put into your mind. Or you can use 2 degrees of freedom PID controller that we'll get into, where it moderates but doesn't completely eliminate the proportional action on a set point change to kind of achieve this benefit of reaching set point quickly but with minimal overshoot. So the time for the PV to reach 63% of the set point change is the closed loop time constant, which is lambda for self-regulating process tuning rules. Remember, lambda for near integrating is a rest time, which is very important. For fast self-regulating loops, we can focus on lambda being a closed loop time constant, which is the way it is in internal model control. Now, the rise time, the time to reach set point, like I say, for me was important, would not be important in bioreactors and fermenters. Fermenters, batch times 1 to 2 days. Bioreactors could be 1 to 2 weeks. If it takes another 20 minutes to get to set point, it's of no consequence. They're more interested in overshoot. But for me, in my chemical processes, it tended to be a consideration, and so here this is what affects the rise time. First of all, you can't get to set point any faster than dead time, and then the integrating process gain, whether it's true integrating or near integrating, determines really that multiplied by the change that you get in controller output, with realizing there's a maximum change based on output limits that you can make, and then you can have control action, feed forward action on the set point change. So you can estimate, and it's not so much you're going to use this equation to provide a detailed estimate, but you're going to look at, well, what is relatively affecting that rise time, and make some judgments as to that, what you should do. Now, let's look at the ultimate limit to performance for a process input load disturbance, and we mentioned that the peak error, the ratio of it to the open loop error, and the open loop error is the fastest and largest load disturbance, is based on this ratio of dead time to the dead time plus time constant. And then the integrated error is a kind of a simple expansion of that. Very simply, it's the same sort of relationship, except now in the numerator is the dead time squared. So you can see that your goal is to reduce dead time, and you can proportionally reduce the best you can do in terms of peak error, and you have a squared effect in terms of the best you can do in integrated error. For a sensor lag or signal filter that is much larger than the process time constant, the unfiltered actual process variable error can be found from the equation for attenuation. So this time constant here it's not making any judgment where it's coming from. We want it to be in the process, but it could be in the automation system. And if it is in the automation system, things are going to look better, but they're actually worse in the process. And we can use this equation here, a very simple equation, to estimate what we're seeing as a filtered amplitude based on an original amplitude and then an oscillation period and a time constant associated with a filter, electrode, a thermal well lag. And we can also use this equation to see the effect of smoothing out oscillations by a mixed volume resonance time. Now, what I tend to do with, in terms of the effect of automation system filtering is to solve for the original amplitude here so that I have a better idea of really how bad it is, because we get this delusional effect of things looking smoother from a filter time constant or a slow electrode or slow thermal well lag when the process is actually doing worse. And it's also useful besides that for understanding how volumes attenuate variability. We got to realize that though, again, for measurement lags and filters, we're providing a very attenuated view of the real world. Now, we talked about the ultimate limit, how good we can do. Let's talk about the practical limit. And the practical limit really depends upon your tuning. And this is why you want to get the tuning right, because even if you have done a great job in terms of reducing dead time, you're not going to do well if you tune the controller sluggishly. And you can kind of understand that that's the situation. But this quantifies it. Originally, I had an equation from Peter Harriet for a proportional link controller, and I reformulated it here. And notice it only takes into effect the controller gain. It doesn't take into effect the derivative setting or the integral setting. Now, I have a more complicated equation that will show that, but that effect is rather minimal, and so I think we can just focus on that most of the effect in terms of reducing peak error comes from the controller gain. Now, if we're talking about the integrated error, it also depends upon the integral time besides the controller gain. And this also has the benefit of showing the effect of PID execution time, delta Tx, and a PID filter. And this comes by courtesy of Greg Shinsky. However, I needed to reformulate it to put it in a more understandable form, as is shown here. So the peak and integrated errors cannot be better than the ultimate limit, but the errors predicted by these equations for an enhanced PID and dead time compensator cannot be better than the ultimate limit set by the loop dead time and process time constant. In other words, if we use an enhanced PID or dead time compensator, we can use really high gain and small reset times. This would lead us to believe we've done a tremendous job, but we're still and we are doing a good job, but we're limited by the ultimate limit. So these equations do not apply to dead time compensators or an enhanced PID where we have really pushed the PID beyond what normally it is capable of doing through these PID options. So we can see that dead time is the key. I say without dead time I would be without a job. The controller would immediately see and correct for low disturbances and set point changes. There would be no high limit to the maximum controller output. No limit as to minimum reset time. Control could be perfect if there was no noise or interaction. And then you can see here how we use dead time for determining lambda for tuning. And whether you're using lambda tuning or other tuning methods, you'll find, or they should be, using their tuning settings as a function of dead time. The other thing is the ultimate period is, in other words, if we, the critical frequency or the oscillation that you get if you had too much proportional action and you didn't really have any integral or derivative action, you were just seeing the effect of the PID gain exceeding the ultimate gain. That would be the ultimate period, and it would be 2 to 4 times the dead time for self-regulating processes. And it would be 4 times the dead time for other processes like integrating, using that first order plus dead time approximation. Now, resonance can occur for oscillation periods between 2 and 10 times the dead time. And the scan time and PID execretion rate should be less than 1/10 of the dead time, and we learned before that the filter should be less than 2/10 of the dead time. And finally, oscillation periods greater than 10 times the dead time are indicative of too low of a PID gain and valve problems, backlash, stiction, poor position, or designs. So how do we minimize measurement dead time? And I kind of focus on that first because, we may not be able to minimize process dead time, although we should in some cases by helping the process or mechanical engineer, particularly in pH control. But what's under our control is the automation system. So what can we do to minimize the amount of dead time we add from the automation system? So this equation shows you the different sources, and it's not like I propose you try and calculate this exactly, but to understand where the dead time comes from and to get an understanding of the relative size. So what you want to do is find out the biggest contributors to dead time and see what you can do to minimize them. Now, for wireless transmitters, the dead time introduces about 1/2 of the update time. For analyzers, since the result is at the end of the analysis cycle, it's 1.5 times the cycle time. And then you may have a multiplexer, so you have to add in another 1/2 the multiplex time. So you can see that can be quite large. Sensor resolution is pretty tricky. And it's not understood or even recognized, and tough to estimate because you got to know what the rate of change is of the process variable, because that's going to be the denominator here that's determining the dead time from the sensor resolution or threshold sensitivity. Okay. Very quickly, we're going to look at resonance. And a key thing to focus on here is that the Brown oscillation is with the PID and manual. So the PID and manual, that shows you the source of the oscillation that's happening from another loop. And so the question is, when we put it in automatic, does it do better or worse? Well, it gets a little tricky because, and the reason I like to show it in manual, because if we get down to an oscillation that's very fast, it gets filtered by the process time constant. But if we get in the range here where we get into resonance, notice how, particularly for the PID gain being 1 times its maximum value, how we get a lot of amplification. And we can reduce that amplification by decreasing the PID gain. Now, if we reduce the PID gain and we get into slower oscillations, we see that, hey, with the higher PID gain, we have less of an amplitude. And now we have more of an amplitude as we're reducing the PID gain, for these slower oscillations where we don't have resonance. And now we're looking at even slower oscillations with loop period 10 times the ultimate period. The load period is 10 times the ultimate period. And this is a much larger time scale on this trend. We can see how much better the higher gain does. And then if we get into a really slow load oscillation where it's 40 times the ultimate period, we can see that we barely detect it with a high PID gain. It's doing its job of correcting this slow oscillation. And again, if you look at the brown trend, that's with the PID in manual. Now, what if we say, hey, we like that high PID gain, but we go too far? We can get into an oscillatory behavior. And here we see that if we just go maybe 50% larger, we start to see an oscillation. If we go 75% larger, it really becomes noticeable. And then if we go twice that maximum PID gain, wow, it takes a while for it to actually decay out. But notice the amplitude here doesn't look too large. Now we look at true integrating, and it actually gets more sensitive. And we see something happening as the beginning. When we increase it by 50%, we get a faltering. And that's characteristic of too high a PID gain, most noticeable in a near integrating, true integrating environment, and also in a runaway environment. And so the oscillations are really not decaying out here for a runaway, so we have to be particularly careful. So if a loop is oscillating, should we decrease the PID gain? Well, we're using the same scales here, and we're showing the effect of, with the same reset setting, what happens if we decrease the PID gain. And notice the amplitude is much larger of these oscillations, and the oscillations get worse as we decrease the PID gain. With them being, and they don't decay as quickly as, and the period is incredibly slow, which means that it's not very well affected and filtered out by process volumes. And here we see it for a true integrating response, it's even worse, and then, of course, as you might expect, for a runaway, it's very bad. And then we have a similar situation, in a way, where low PID gains make oscillations worse if we have backlash in an integrating process. And if we have the PID gain we're entitled to, there's still an oscillation. But it gets a lot worse as we decrease the PID gain. It gets quite large. Now, not shown here is the effect of backlash in a self-regulating process. It turns out we can get into oscillations very readily in a self-regulating process by too low a PID gain. And if we just use the PID gain we're entitled to, we can actually eliminate oscillations from backlash in the self-regulating process, which is not what we've got shown here. So that's the end. I'm sure that's quite a bit of material for you guys, and we're actually going to get into how we look at finding that window of allowable PID gains, because now we recognize that too low a PID gain as well as too high a PID gain can be problematic for near integrating, and one-way processes, or where there's backlash in a control valve. So we'll go back to the main screen. Wow, we still have people here. And I forgot to say you could ask questions, but you sure can ask them now. That's a good question. In Provox and in many systems, you probably couldn't adjust it. Delta V we can, and so should we adjust it? And I think if you had a valve with a lot of backlash or stiction, I would consider increasing it, and but you would have to be a little bit concerned that if you increase it too much and the valve jumps. Actually, you want to get the change in output large enough to get through the backlash deadband or the stiction resolution. But if you do it too much, then the valve is going to jump. And if you're doing this a lot of set point changes, it can wear out the valve, but maybe more importantly, it could upset another loop. Say that on the same header, say you're manipulating a utility flow and there's other people using those utilities, and so you make a sudden burst in that utility flow, it could affect other control loops. Yeah, but normally we don't. The benefit, hopefully what you ought to do is get a better valve. You know, just as a practical matter, you know, you could use it that way. I don't think it helps you get the set point that much faster. I think that it's more the benefit you get from the PID gain being larger, that being a sustained step change that gets you to set point faster. That's a good question. Appreciate it. Now, we're going to finish up these slides in part 3, and we're going to get into different PID structures. And actually, the very last slide is for what is, I think, the best structure, but it also is probably the most confusing structure, and that there's nothing really out there that fully details what I've got shown, and it also is the key to some PID options that we're going to talk about that are extremely beneficial. So I know you probably can't wait to see that last slide, but that'll be the end of part 3, which will be the end of this presentation, and that'll be next month on a Wednesday again. And is this time okay? I mean, I like this time better, but I haven't heard any negatives. But if this time doesn't work out for you, let me know. Thank you, guys.